Well, thank you for everyone being in the room today. I'm going to talk about Apache NiFi, obviously, and how to use it to run visual quality inspection. So I'm going to go through a real use case we have in the manufacturing industry, but it can actually apply to many industries. So about myself very quickly, I'm currently a customer engineer working at Google. And I'm involved in the Apache NiFi community for the last 4 years. My Twitter and GitHub accounts, and if you already know about NiFi, maybe you went across my website. By raising your hand, how many of you already know about Apache NiFi? Cool. And how many of you used it in production or real use case? Great. Okay. So in this talk, I'm assuming you already know a little bit about NiFi, so I won't go too deep, but if you have any questions, we can discuss at the end. Feel free to ask any question. So a little introduction about NiFi, nevertheless. So initially, it's been developed by the NSA 30 years ago, and it has been open sourced and donated to the ASF in 2014, and it became a top-level project 4 years ago. What is NiFi used for? So I was actually discussing it with someone at lunch. Usually, people I talk with have a lot of difficulties to position NiFi against ETL tools, streaming tools, PubSub messaging tools. So it's let's say, from my point of view, if I had to give a definition of NiFi, it's a toolbox with a lot of tools to move data around from a place A to a place B very efficiently with a lot of features like multi-tenancy, data lineage, data provenance, stuff like that. So you really need to see NiFi as the tool you would use to get data available and cleaned, processed, to make it available for consumption to someone else. That's how I would picture it. So usually, yeah, you can use NiFi to move data around from the edge to your core infrastructure, and you can use a lot of NiFi instances along the way. So NiFi is a big project. We have a lot of sub-projects very quickly. So NiFi is the core project. That's the one I'm going to use extensively today. MiNiFi as well. So it's a low footprint version of NiFi, aimed to run on IoT devices. So I'm going to use the Java version for this talk, but obviously the C++ version is way more adapted for real IoT use cases, because obviously you don't have always a JVM available. Then you have the NiFi registry, which is used for everything around CI/CD for NiFi. So when you need to move your workflows from an environment to another one, you will use it to version your work when you publish new version of your workflows. You can also version your extensions, because NiFi is a very extensible framework, so you can actually build everything by yourself if you have very specific needs into NiFi. C2 server is command and control for all the MiNiFi agents, and fluid design system is for the UI parts that we are trying to make reusable across all the projects. So right now in NiFi, you have about 300 processors to integrate with a lot of systems. That's the processors we are shipping with NiFi when you are downloading the binary files from the website, but you can actually find a lot more processors on the internet. One I can think of, and we had a talk about it yesterday or today, is PLC4X. We also have Apache Pulsar. So a lot of projects have processors not shipped by default, but still available on the internet. Usually I put this slide at the end, but I wanted to put it right now, so we don't skip it at the end. So the Apache way, community over code, I believe Apache NiFi has a very great community. So if you want to subscribe to the mailing list or contribute or participate or ask questions, you have everything here. Usually we would use the mailing list as a primary way to reach out, but you can also use the Slack channel. A few numbers. So right now on the Slack channel, we have over 500 people. 260 contributors on GitHub across the repositories because, as I said, we have multiple projects, 45 committers. Since yesterday, we have the Apache NiFi 1.10 release candidate under vote. So if you want to download it, build it, and cast your vote, feel free to do it. And on Docker Hub, we are reaching 1 million Docker pools for the Apache NiFi Docker image. Okay, let's go into the use case. So I took a use case that I could easily reproduce at my place. So in this case, I'm going to detect if cookies are broken or not broken. So picture a factory where you have production lines and you are making cookies, and obviously you don't want to have unhappy customers. So before the cookie gets to the packaging, you want to get the broken cookies out of the factory line. So to do that, we can use NiFi. And with NiFi, we are going to use some tools provided by the Google Cloud platform. And specifically, we are going to use a combination of AutoML and Cloud Vision. So, well, that's usually what I present to customers when they ask about machine learning at Google. So we provide a wide range of solutions, and depending on how much you want to do everything by yourself, you have the solutions. AutoML is in the middle of CloudML. CloudML is where you build your custom models, but you need to know about models, about your data, about what you want to achieve. And on the right, you have the APIs ready to consume, where you don't have anything to do, and you probably know about translate, etc. AutoML is in the middle, so you are going to provide your data, and we are going to train your custom model, but you don't have to do anything else. You don't have to say anything about your data. It's going to train and optimize the best machine learning model available for your need. What we are trying to do here is to have a continuous model retrain, including a feedback loop. So when we have trained a machine learning model, that's great. We are deploying it on the edge, amazing. But obviously, your model is going to evolve because maybe you are going to detect new features with broken cookies that your model is not able to detect. So you want to retrain your model with that new feature. So we actually want to have this full automatic loop where the pictures we are taking are ingested into Google Cloud, and we are training again a new model and exporting and deploying this new version of the model. So that actually the model gets better and better over time. Now, how we can do that, and if possible, in an efficient way. So first, dummy solution. So we are running MiNiFi on the edge on a Raspberry Pi here. Just quickly, I won't do any demo because I don't want to take broken cookies everywhere here. But if we want to discuss it, I have everything running, so we can talk about it. I will stick around after the talk. So we have MiNiFi running on the Raspberry Pi, talking with Google Cloud IoT Core through MQTT, which is the gateway for IoT, basically. The data is sent to a pub subtopic, which is the Google equivalent, let's say, of Apache Kafka. Then we have a NiFi running in GCP that will take this data, do some processing. We will go into the details, make it available to Google Cloud Vision. And then I'm using the first option, which is Google Cloud Vision is actually exposing the API that I can request to classify my images. So in this case, I am not deploying the model on the edge. It's available in the cloud, and MiNiFi is doing an HTTPS call each time we want to classify an image. It works. Obviously, we will see that it's not efficient, and it's assumed that your MiNiFi is able to do an HTTPS call to Google Cloud, and obviously, most of the time, we don't want to do that. Second architecture, so it's quite the same. So communication through MQTT with Google Cloud IoT Core, but when we train the model in Google Cloud Vision, we are exporting the model and make it available directly on the edge, and the inference, the classification of our image, is happening directly on the Raspberry Pi, which is much faster. Okay, so the first step is to actually create a data set and register your device. So that's the device. I won't go into the details, but in Google IoT Core, you can set up your registry, which is the collection of devices you want to manage. Then you register your device with the TLS certificates for identification, authentication, and stuff like that. So not very important. Then here is a workflow that is actually running on the MiNiFi part. So each time when you see a NiFi workflow, I'm specifying on the top where it is running. So this one is on MiNiFi. So very easily, I'm saying to the Pi camera to take pictures with the code over there. Nothing fancy, very basic stuff. I'm taking the files and sending the pictures through MQTT. That's it. So once the images arrive to Google Cloud IoT Core, as I said, you don't have to do anything. It's automatically pushed to a PubSub topic. And then on my NiFi running on GCP here, I have another workflow, which is pulling the data from the PubSub topic and putting this data into Google Cloud Storage. And then on the right, I'm doing some API calls to make this data available to Google Cloud Vision. Great. So here is what I did during my last few days. I have exciting days. I took hours to take pictures of cookies. Really great. But here are the pictures. This is the UI of Google Cloud Vision, which is currently in beta, but it will be GA before the end of the year. And you can actually go over the pictures and label your pictures. So in my case, I said that I have only 2 labels, not OK or OK. I have labeled images, unlabeled images that I just ingested, but I didn't say if it's OK or not. And that's it. Once you have at least 10 images per label, you can actually start training your models. Then, what I want to do is to be able to switch from the architecture 1 to the architecture 2 just by configuring my device from the GCP platform. So on MiNiFi, if you remember, this is the processor where I'm sending the images through MQTT. So when you connect to MQTT to Google IoT Core through MQTT, you can also receive configuration changes and comments. So in that case, this is the workflow I defined to take care of configuration changes. And here is a JSON representing my configuration. So you don't see anything, but basically I'm saying in which mode the device is running. Either cloud mode, so the Raspberry Pi will make an HTTP call each time I capture an image, or edge mode, the model is running directly on the device, and I'm doing the inference locally. Then, on my workflows running on the NiFi on GCP, I externalized all of the variables I needed. So I won't go into the details, but basically you also have the mode here, which is either edge or cloud. The other variables are just some parameters I externalized so that I can manage everything in one place. Okay, model training. So as I said, I don't want to do anything manually, so I have a workflow taking care of the model training. So every day at midnight, I'm triggering a new model training to get a new version of my machine learning model. So I start the model training by making some API calls, waiting for the completion of the model training, and then I will take care of the deployment. So once you have made the API call, if you go into the UI, it will look like this. So you actually see that the model is currently being trained. And at the end, you will receive a JSON answer like that, saying that your model is ready. and you can use it. So once the model is trained, on the UI, you can have a lot of information about how efficient the model is going to be regarding confidence. You also have the details if you had true positives or true negatives, etc. during the validation of the model. So everything is available. I won't go too much into the details here. So architecture 1. So as I said, in this case, we are just deploying the model on Google Cloud, and an API is made available for you, and you can just call the API with your image to get the label on your image. So this is the second part of my workflow running on NiFi. So in case I'm in the cloud mode, I'm doing the API calls to deploy the model on Google Cloud, and it's made available. So it's in serverless, so you don't have to care about servers, how it is made available, on what it is running. Google Cloud is taking care of everything. Okay. Then once the model is trained, I have to say to my device which model to use. So at the end of the workflow, actually here, at the end of the workflow, I'm executing an MQTT command to send the information back to my device. So I'm sending to the device the model ID that I just trained. And I make this information available on my device. Again, I won't go into the details. It's not really necessary, but just a few processors to receive the command and extract the information. So that was the architecture 1, then the architecture 2. So in this case, we want to actually export the model directly on the device. So quite similarly, we are calling the API to make the model available on GCS, Google Cloud Storage. And then we are sending an MQTT command to the device to say, okay, my model is available and you can download it here whenever you want. So same, I'm receiving on the device this information with the Google Cloud Storage path to download my model, and I'm downloading the model directly on the device, and now I can use it locally. Inference. So now we have everything. We are able to start the loop. We have the first version of our model, so we can actually start doing some inference. So here is what it looks like on the MiNiFi part on the Raspberry Pi. So in this case, I'm doing the inference in the cloud, so making the API calls, and we can see some examples of the results we are getting with the label we are computing on the picture, confidence score, and the mode in which the device is running. Okay, now we can do the same. If I switch the device to the other mode, Edge mode, I'm using the model directly, locally on the device, and I can do the same. So I'm executing the model. It's a TensorFlow Lite model, so you can execute it using a very short Python script, and you have the same results. So each label with the confidence score, and that's it, basically. Okay, that's great, but now we want to do more. So actually, you can get even faster in your inference using Google's TPU. So TPU stands for Tensor Processor Unit. That's hardware that Google is making, and only Google is making this hardware, and you can use it to actually have even better performance for all your TensorFlow models. So in this case, I used the USB accelerator, which is here. And great news, yesterday, this website came out of beta. So it has been announced yesterday. It was not planned. You can look at all the examples, resources on the website, and get some board looking like Raspberry, and also the USB accelerators, camera, and stuff like that. So some results when I'm running what I just showed you before. So when I'm actually running my workflow on my Raspberry Pi and doing the inference using the first architecture. So between the time I take the picture and the time I have the label, it's about 6 seconds. The HTTP call itself is about 2.5 seconds. So obviously, in a factory, if you have tens of cookies per second going on your factory line, you cannot work like that. So then, if you go with the model on the edge, the processing time between the picture, I take the picture and the moment I have the classification, which is the cookie is okay or not okay, it's about 550 milliseconds, and the inference time itself is a bit more, 100 milliseconds. And then when I use the USB accelerator using the Edge TPU features of Google, the processing time between the picture and the labeling, it's half a second, and the inference time itself is below 10 milliseconds. So here is an example, just not to throw a number like that. So the first one is when I'm using the model that you will download from the Google Cloud Vision API, which is not optimized for Edge TPU, and you will get the numbers here for the inference. And then you can also download another model which is optimized for Edge TPU, and you have the inference time, which is around 9 milliseconds. Okay, so that's great, but you could say, I don't know what's going on my device. I don't have any monitoring capabilities. With what you showed, it means that each time I'm taking a picture, the picture is ingested into my dataset in Google Cloud Vision. I would have to manually label it to actually use it for the next version of my model. So we have some rooms for improvement. So first, what I'm going to do is to automatically label the data if I'm confident enough on the labels that I inferred on the picture. So for instance, if I take a picture of a cookie which is okay, and I'm confident at 99% that the cookie is okay, I don't want someone to label it. I want to push it into Google Cloud Vision directly with the label and take it for the next training of my machine learning models. Also, something I can do is to send the inference results along with the pictures through MQTT so that I can make monitoring on Google Cloud and also detect outliers, inference performance, and stuff like that. So I did it. It's making the full workflows a little bit more complex, but I won't go too much into the details. But basically, before going to the IoT device MQTT processor, I'm doing the inference here. And I'm sending this information through MQTT to Google Cloud. So once I do that, I'm able to do some monitoring dashboards in Stackdriver, and you can actually see what I was showing before. So meaning that here, the inference is happening in the cloud. It's architecture 1, and it's about 6 seconds. And then I switch the mode, and the inference happens on the edge, directly on the device, and it's below 2 seconds. Same for the confidence. So you can notice that when you are doing an API call to Google Cloud Vision to get the label, we almost get a score of 1, so 99% of confidence. But as soon as we build a machine learning model that is designed to run on the device, we have to reduce the size of the machine learning model, so it's going to be efficient with the low latency for the inference, but obviously you lose in accuracy of the model. So once we are doing the inference on the edge, usually we are around 90% of confidence when we are doing an inference. On the right, you see the switch between using the accelerator and not the accelerator. So first the accelerator on the left. So I don't know why, to be honest, but actually when we use the accelerator with the model which is optimized for Edge TPU, we have a confidence score which is higher than before, and we have an inference time which is lower than before. So you have no reason not to use it. Obviously, but I won't go into the details of that. Once you have all of the data into Google Cloud, you can perform analytics. You can do whatever processing you want on the data you are collecting if you want to do something. Okay, so a conclusion. So with NiFi, in combination with GCP, we did implement this feedback loop, which is working automatically. Actually, you don't have to do anything once it's started. So you did everything without writing any code, except the Python script I showed at the beginning to take pictures. You have the feedback loop. You don't have to manually do anything except for labeling the pictures that are below a given threshold that you want to actually look into. And you can do the processing on the edge using TensorFlow Lite and boosting your performance using the Coral Edge TPU. And that's it. Very quickly, before you go to the questions, I went through the slides very quickly, and I didn't go into the details of the workflow, but I will be publishing everything on a GitHub repository. I started writing it yesterday evening, so right now, not too much on it, but I will work on it tonight and tomorrow in the plane. Anyway, everything will be available on this repository: code, workflows, processors. I will make everything available, and so you can deploy it and play with it very easily. And that's it for me.
Thank you, thank you. Questions? Must be, please.
I know it was easy, but come on, you have questions. Thanks. Here?
You had this inference processor. This was a custom processor written by you, or?
For the inference itself, it's just a Python script.
Oh, okay.
So it's actually available on the Coral website.
Okay.
I didn't change anything on that.
Just plug it in and
yes.
you're done.
And you give the parameters I showed, the model, labels, and the image you want to classify, and that's it.
Okay.
And when you use the Edge TPU, you have a little bit of installation to perform a setup, but I mean, it took 5 minutes. Very easy.
Okay. Thanks.
Reminds me.
A lot of questions over there.
Okay. While I'm going there.
Yeah.
The processing time that you had there, you can multitask the same module.
Yes.
If you multiple cameras, you can schedule.
Yes.
Okay.
You calls. And I remember that I have to repeat the questions. I've been asked to repeat the questions.
It's not really a question, just a side note for the previous question. Do you hear me?
Little bit.
So just a side note for the previous question that in the C++ MiNiFi, we added the OpenCV module so you can connect to whatever video source and capture image and detect motion without needing to write a line of code.
Yeah. Yeah, so yeah. I mean, obviously, it's because I'm lazy that I use the MiNiFi Java option, but you can do exactly the same with MiNiFi C++ version, and you will be able to run it on something else, that Raspberry Pi, and on very small devices or IoT stuff.
I wanted to know if there are significant cost differences with the 3 different ways in GCP.
So right now, given the fact it's in beta, it's not very costly, but actually, as a user of Google Cloud Vision, I received an email yesterday or 2 days ago saying, we remind you that this product is going to be GA before the end of the year, and this is going to cost that much. So I don't remember the prices, but you pay for the training of the model, which is not very expensive. Obviously, depends how much images you have in your dataset and how long it takes to train the model. And you have a lot of parameters. You can tune the model based on your needs and also based on where your model is going to run. And if you deploy the workflow in Google Cloud and expose the API, you also pay for each call that is made to the API, but it's very low. as far as I know. Yep.
Could you elaborate a bit on the MQTT protocol, what it's used for, and what I didn't get quite clearly what was the messages exchanged?
Well, MQTT is basically one of the protocol which is the most used for IoT communication. And if I remember correctly, you have two options for Google Cloud IoT, MQTT and HTTP. I'm not sure about this one. Actually, so if I go back very quickly, sorry, here. So actually, this processor right now is not available in NiFi by default. This is a pull request I made a few months ago. It's not in the code base yet, but I will make it available on my repository. But you already have a MQTT processor available that you can use with AWS, Azure IoT, and GCP. I mean, MQTT is the protocol that you will use with IoT for most of the cloud providers to get the data and also to send information back to the devices.
It's fully generic. You can send an image, you can send a prediction, whatever. Sorry.
Well, it's a protocol, so you send whatever payload you want. In this case, in the first version, when I'm not sending the inference, I'm just sending the bytes of the picture, really the picture itself. And in the version later, when I'm sending also the inference results, I'm sending a JSON payload with the inference results and the image with the base 64 encoded.
Yeah, I hope this is not too basic question, but you had a lot of steps, and some of them were sort of executed on the edge, some were in the cloud. And so, how do you sort of define in NiFi and tell it where to run which parts?
Yeah, there is no dumb question. Don't worry. So, well, basically, MiNiFi is a low footprint version of NiFi, and on MiNiFi you don't have any UI. Okay, so. When you want to deploy a workflow on MiNiFi, you usually develop it on a NiFi instance, then you export it, convert it into a YAML file, and then deploy it on your device. That's usually what you do. And if you also want to actually deploy new versions of your workflow on your devices, you would use a combination of NiFi registry and NiFi C2 server. That's something I published, an article I published a while back, but yeah, that's something you can do. But here it's just for clarity. This is what I design on my NiFi instance, but then for the MiNiFi part, I'm just exporting it and deploying.
Okay, because every slide I've seen on NiFi, there's always this part where there's a dotted line and it says, well, this is on MiNiFi now. And I just thought you sort of configure that in the IDE. You don't.
No, actually, so in this case, when I did it, I developed my workflows, exported it on my laptop, and then SCP the file on the device, restarted MiNiFi, very basic stuff. But you can do it fully automatically with the NiFi registry and NiFi C2 server, which means that actually in NiFi we have a notion of what we call templates. So you can actually save a workflow as a template. Then the C2 server is gonna detect a new version of your template. This template is gonna be downloaded and forwarded to all the devices. And then the new workflow is used on the devices as the new workflow that MiNiFi should use. But again, there is no UI on MiNiFi, so you have to develop the workflows somewhere else and then deploy the workflows on MiNiFi agents.
Well, thank you.
Yeah, you're welcome.
Thank you.
Someone suggested that I should have brought cookies and shared cookies with you, but I didn't.
Real-time cookie classification. Yes.
Well, thank you.
Thank you again, Pierre.
Yeah.